poster gate. I was able to get Michael Toomey responded, so we're filled for the May 1st seminar.
Awesome. Okay. Yeah.
All right. So go ahead and get started. Okay. So we're very happy to have Matt McQuinn here this week. It's the whole week, right?
Yeah, whole week.
Excellent.
Yeah.
And he's going to be telling us today about some cool way to measure Hubble constant with some new ideas. So without further ado, take it away.
Yeah, thanks so much for having me. It's a pleasure to be at your department. This is a super small group, so if you have questions, please just interrupt. And in fact, I prefer it that way. What I'm going to be telling you about is a paper that came out about a year ago. It's by far the longest AppJ letter I ever wrote. It's 20 pages. And it definitely describes something that's kind of out there, a concept. And so just to legitimize it, I will also tell you that it recently received this cosmology prize that was announced at AAS, the Buchalter Cosmology Prize. So one thing I struggled with, like when thinking about presenting to you guys, is this is like the most cosmology-focused astrophysics group that I'm aware of. So I think the first few slides are going to be a little bit on the intro side, but I think it'll be fine. But you guys can yell at me if it's too slow. I'm going to start off with a plot that was really made kind of at the dawn of cosmology as a science. This is Hubble's 1929 diagram. The velocity is plotted on the y-axis. Of course, velocity is easy to measure in astronomy. But it's looking at the Doppler shifts of lines. And then distance is the x-axis. Distance is harder to measure. Usually we find some object where we think we know how much power it emits, and then you measure flux on a detector, that gives you distance. Hubble had a bunch of ways of doing this. His favorite was these Cepheid variable stars, where we think we know how much power comes out.
Although these are very crude, right? Like these are like, take the brightest star-like thing in the galaxy and assume that they're all the same.
Yeah, actually, yeah. I think he had a few methods, right? He would find the close things would be the Cepheids, and then the middle. I think it was the brightest thing, which ended up being star clusters, but he didn't realize this. Yeah. And then it was like groups of galaxies out here.
Yeah, I think you did the same thing, but in group. Like you see, you have 4 points.
Object in a group.
Yeah, you have 4 points at the same distance. Those are all the same group, right?
Yeah, that's right. So there were a variety of methods. All where you're trying to figure out what the power is.
Do you know his error measurements, or like what are the error bars on this?
Well, none of this is cosmological, right?
I mean, he said clearly this follows a line, and so this is Hubble's genius, and he said
the slope of that is 500 kilometers per second per megaparsec. 500,
okay.
Yeah.
Yeah.
But it's all local group, right? And the horizontal axis.
Well, no, it's further than the local group because it's it's a factor of 5. It's a factor like 7 wrong. So 2 megaparsecs there is actually like 14 megaparsecs.
Yeah. So these are all really close galaxies. And as Mike said, like we could just read it. So he drew a line. Said velocity is proportional to distance. As you guys know, this parameter, the slope we now call the Hubble constant, and we could just read off his measurement, which was the most wonderful 500 kilometers per second at 1 million parsecs a megaparsec, so 500 kilometers per second per megaparsec. And this constant has had a tumultuous history, and so 500 kilometers per second per megaparsec, we've gradually find some of these mistakes. And there was a period of time where there were two camps. There was a camp that was arguing whether it was 50 kilometers per second, and another 100 kilometers per second per megaparsec. And then gradually, we converge on something that's in the middle of those, like something like 70 kilometers per second per megaparsec. And as you guys have all heard, there's this tension where the error bars are smaller than the differences between the measurements, and this is the Hubble tension. Okay, and I'm going to be just very brief, but this Hubble tension is we have these direct methods for measuring the Hubble constant, just basically making this Hubble diagram and measuring the slope. And we have less direct methods where we take our cosmological model and we fit the cosmic microwave background, anisotropies, for example. And when we do this, we have some model that has 6 parameters, our lambda CDM model, and one of the parameters in that model is the Hubble constant. And so when you do that, we're finding something that's low compared to the more direct inferences, and so this could either be
So
yeah.
So you do use the CMB, but you cannot do that measurement without the large scale structure surveys, unless you assume it's flat and there's no evolution in.
Yeah, I mean we've assumed it's flat.
You've assumed it's flat, but the only reason you know it's flat is because you have the low redshift observations.
And you have a
right?
inflationary prior to that could be flat.
Oh, great.
Your inflationary prior there tells you that lambda is 0, right?
Yeah, there's a lot of inflationary priors.
Well, I don't think that inflation, having a like vacuum energy dominated era early, that makes a lot of sense. So that I don't think it says anything about late.
I remember the 90s. It was so surprising.
Our prior is that it's
theorists.
super small or super large but okay. This is not.
All I'm saying is just
we don't want to go here.
Just say large scale structure and the CMB.
Oh, okay.
That's the only accurate way to say it.
I will be careful for the rest of this talk, Mike.
Oh no, the rest of your life. I'll always be there.
Yeah.
Could you do a N plus?
Yeah, if you believe it's supernovae, but yes.
Okay, but how do we make progress? And actually at lunch we discussed one possible way of making progress is that there's some systematic, and actually that seems like the nearest term progress on this Hubble tension is going to be if we find some systematic, and our smallest error bars with these Cepheid calibrated supernova, and so if this is going to be resolved in the next 5-10 years, I think that's kind of what has to happen. Of course, it might not be a systematic. It might be that there's some underlying assumption when we fit this lambda CDM model that is not correct, and so that would be the more interesting scenario. If we don't find some systematic in the next decade, then I think we really have to wait for these gravitational wave detectors, the next generation of gravitational wave detectors, and in particular these neutron star mergers, where again you're doing something similar to for example supernova or Cepheids, where we know the power that's emitted when these neutron stars merge, and it seems like it's cleaner physics, cleaner gravitational wave physics. And we had this example from this 2017 event where that provided a 15% measurement of the Hubble constant. But we think we were very lucky with this example, that we were fortunate to have this event that was so close. And it's kind of unclear, even for the next generation of these 3G gravitational wave detectors, whether how many of these events they will get, whether they will have enough with electromagnetic counterparts to really push to the 1% constraints that we have with the methods that I was showing you. Okay, so today we're going in a totally different direction, and I'm going to discuss another possibility. It has the advantage that it's totally geometric for measuring distance. It has the potential for scaling up to extremely high precisions. It also has the potential for not just measuring the Hubble constant, but measuring the expansion history. And then there seems to be a lot of other interesting science that you might be able to do with this idea. And as you guys know, this is again Hubble's diagram. Like this is velocity, this is distance, and as you go further out, not only are you sensitive to not only is there a slope to measure, but it how the universe expands with time affects this relationship. And so, and for example, by measuring this is how we discovered the dark energy was discovered in 1998. And so why would you want to measure this better? Well, one of the reasons would be to constrain the properties of the dark energy. Maybe to discover that the universe isn't flat would be another reason. And maybe this has gotten even more interesting or more motivated in the last week with this DESI result that at least they're finding that from BAO measurements that their measurements are not consistent with a cosmological constant at currently 2.6 sigma, and it actually even the discrepancy increases if they include supernova data. Okay. All right, so that's all the intro. That's the motivation, and now we're going to ask the question: how possible is it to do parallax measurements to extragalactic sources? But before I do that, are there any questions? Yeah.
The other possibilities of measuring Hubble, like with IPT, Lancet telescope, right, that you mentioned, are they also able to get H naught at different redshifts as well, or Hubble at different redshifts?
Yeah, actually, I think a lot of their events will be at redshifts of several tenths to 1. And so I think the predictions are that it will also constrain dark energy properties well. Other questions or comments? Okay, parallax. Okay, as you guys know, as we go around the sun, if you look at some astronomical object from from this side of the sun and this side of the sun and measure, it will move on the sky depending on how far away it is, and that angle we call the parallax angle. And so if we measure that, we're via basic trig able to figure out how far away the object is. If it's closer, it'll move further as we go around the sun. And so we've been able to do this with Gaia out to distances of 10 kiloparsecs. But really, in order to precisely measure the Hubble constant, you have to do this at distances greater than 100 megaparsecs. And the reason for this is just because there are local gravitational potentials that are moving things around. And so things have velocities that are not just from the cosmic expansion. And so this adds some noise to when you're making this diagram that becomes less as things are further away. And so we're talking about distances greater than 100 megaparsecs, this noise is only at the several percent level or less. Okay, so what would it take to measure parallax to sources at these extragalactic distances? All right. So if we go halfway around the sun, with 1 AU, like we're just doing a simple parallax calculation. This is the parallax angle. I want what is the angle that object at a distance d, where I'm going to put in 200 megaparsecs for the distance. 200 megaparsecs is the median distance of the Schu's supernova, which gives our tightest constraint on H naught. So this is the number I'm going to use throughout this talk. So just stick in numbers, and you find that this is 5,000ths of a micro arcsecond. So if you can detect that, you're able to measure the parallax to this extragalactic source. Unfortunately, this is 10,000 times smaller than the parallax angles that Gaia has been able to achieve. So we could just do an exercise to ask, like, what the heck would it take to actually measure this? And so how well you can measure an angle is the wavelength of the light you're looking at divided by the size of your telescope divided by the signal-noise ratio that you're detecting the object. And so we're going to do this in the radio because of the direction that this talk is going. So the wavelength I'm going to say is 5 centimeters. I'm also going to assume modest signal-to-noise ratios, again, because of where we're going. Actually, Gaia has really high signal noise, so it's in a different regime on stars or quasars. Okay, so if I take those numbers in, then I'm forced, the x is the size of my telescope, to put in something really large. So then I would need the size of my telescope to be 1 AU for the coefficient here to be comparable to the coefficient here. Okay, 1 AU size telescope, that sounds really big, but in the radio, like we don't necessarily need to fill in the telescope, and in radio we often will call this a baseline. So we could have individual dishes, and if they're separated by 1 AU, this is the error that in this parallax angle. And that's kind of where we're going. We're going to suggest and we don't want to measure things at order unity. We want to measure them at the 1% level, and so we're going to need 10 and tens of AU or larger separations for this to be competitive.
But when you said modest SNR, what's modest?
For Gaia, for some stars, this is like millions. So I'm assuming I'm only detecting something at signal noise 10,
Okay.
which is all below that. You're almost not detecting it.
Gotcha.
Good question. Okay. The other thing, it sounds like this is a pretty extreme direction to go, but I think one interesting thing that I will hope to convince you of is actually the technology requirements, other than putting things way out in the solar system, seem very achievable. Okay, but in order to get to that point, we're going to go in all sorts of directions, and then hopefully things come together later on in the talk. We'll see. Okay, and so first digression is we're going to talk a little bit about global satellite navigation systems like GPS. And so you have your phone. It tells you to meter like where on Earth you are. How does it do this? Well, there are these GPS satellites and they have some carrier wave, and then they modulate that carrier wave with some code. And each satellite has a different code. Your phone knows what the code looks like for all of these different satellites, so it does a match filter like search to lock onto these codes. Once it locks on, it knows the distance to the satellite because it knows when the code was sent. Since your phone doesn't have an amazing clock on it, you need to constrain 4 numbers, you need 4 space-time coordinates, so you need 4 satellites. And once it finds the distance of 4 satellites, it's able to trilaterate its position to meter. Okay. So it turns out that this technique scales up really well. So if I take one radio dish which has diameter d, and I put another at a diameter d dish 100 AU away. In this talk, I'm going to assume either 10 meters or 4 meters for the sizes of my dish. 10 meter radio is not like 10 meter optical, so, as we'll get to. But so we're at two 10 meter dishes, 100 AU apart, and I'm just going to ask how well can they measure the distance between themselves. So this is a well-known form, this calculation for you open up a GPS textbook. And in fact, I've even assumed the same chipping as these GPS codes. And so if you just put in things like if one is broadcasting a 30-watt signal, you integrate for a minute, then they can measure their distance to a few centimeters, and likely much better with optimizations. And actually, we do this. So we've been able to measure the distance to the Cassini spacecraft at 2 meters when it was at 10 AU. So we know the distances to these outer solar system probes pretty well.
So 2 meters and not centimeters?
Oh yeah, actually it's because they only use 1 frequency. You have to use 2 to take out the plasma, and then actually you would be in the centimeter. Good question. Okay, next digression. There are 5 digressions. It's a very long baseline interferometry. This is kind of similar to GPS, but on astronomical sources. So we have some dish on, maybe this is North America, and maybe this is Europe, and there's a quasar, or whatever astronomical radio source you're interested in, and so the light from the quasar will hit this dish before it hits this dish, and so basically there's some, but the waveform is the same, so there's some template waveform that hits this dish, and then when you measure it, and then you can go over to this dish and you can see what delay do I have to assume in order to align this waveform with this waveform. And once you align the two, you've measured this delay, so you've measured this distance. And we know very well how well we can do this. And so essentially you can measure this delay to this error, which is essentially 1 over the bandwidth divided by the signal noise. if your bandwidth, let's say, is a gigahertz, which is a number you'll see later, then we're talking about sub-nanosecond measurements of this delay. And in fact, this has been done to do amazing things. Like you can use this to then measure the spaceline length and study, for example, plate tectonics, and in particular, like baseline lengths across the globe have been measured to the 1/10 of a millimeter per year, like how much they've changed, which is actually much smaller than the actual shifts of the plates. Okay. This is a question for you guys. What is the longest baseline that these voltage correlations, this VLBI, have been detected? Is it 2/10 of an Earth radii, 1 Earth radii, 3 Earth radii, or 50 Earth radii? 50 Earth radii is like the moon distance.
Probably not 3. 3 sounds weird.
Okay. 3 is actually the GPS satellites. That's mid-Earth orbit. It's not that weird. It's not the answer, though. You guys can guess. No shame. You guys are particle theorists.
We already know it's not
cosmonauts.
C.
We wouldn't we guess 1? I mean, isn't 1 the natural unit to guess here?
Yeah.
Yeah, well, okay, that naturalness does not always apply, you guys.
That's not what you were saying before.
But yeah, it's actually 50. There was this Russian satellite that was working to about a little, it stopped working maybe a decade ago, called Radio Astron, which was this 10-meter fold-out dish that orbited out to the moon. And so it did this for pulsars and for AGM. And
What was it
you
compared-
correlate with things on Earth.
Oh, okay.
In fact, you take a big dish on Earth to correlate. Okay. Next digression. Fast radio bursts. You guys are probably, has everyone heard of fast radio bursts? Yeah. Okay, so they're these extragalactic millisecond bursts that were amazingly discovered just a little bit more than a decade ago. Although there was an earlier burst that had been reported in 2007 that eventually was identified with this class of events. We currently know about 5,000 via the CHIME telescope. But the prediction is that this will become millions in the coming decades. There are 10,000 on the sky a day. More than 50 are known to repeat on 10-hour timescales. The projections are that there are really thousands of repeaters on 100-hour timescales. And it turns out that these repeaters are the best source for us because we just want to point at them. Like we want to point at a source that we know is going to go off at some point. And conveniently, the repeaters, many of them we have localized to galaxies because we know they're repeating. We can put an interferometer on them to figure out where they're coming from, and they're at distances that are really convenient for our purpose of measuring distance. They're distances of 100 to 1,000 megaparsec.
So these repeaters, they repeat periodically or just randomly?
They randomly, but on 10 to 100-hour timescales. Actually, some of them just go. It's strange. Like every once in a while, there's one that just goes crazy and repeats on tens of minute timescales or hour timescales. But yeah, but there's a class that repeat.
So basically, repeaters here means that there is more than once coming from
The same source, but it's not periodic. It's not like a pulsar.
And if it comes twice, that's already will be called a repeater.
Yeah, we would call it a repeater. Yeah, that's right. The other nice thing about fast radio bursts is we're talking about these enormous baselines, and we want our source to be a point source for measuring distance. And every other radio source that we could think of would be resolved by these baselines, and so there wouldn't be a point source. The FRBs are small enough. Okay. So the next question is, okay, we want to target FRBs, but are they bright enough? Or how big of an instrument to
So
have
they're,
this.
you know they're small enough just because it is such a short burst.
Yeah, if you say it's not Lorentz boosted, then you're talking about 1,000-kilometer like region.
Okay, but
But
it's
it
the
needs
delta.
to be, to not be resolved, it needs to be less than 10 to the 12 centimeter. So you're still pretty far from that, so you can even have pretty high Lorentz factors, except there's no model that does this. But so it's actually very easily not resolved by.
But it's the fastness of the burst that's telling you.
That's
that.
right, so
Okay.
the fastness means that it needs to be, if it's not moving relativistically towards you, that it needs to be within a 1,000-kilometer region.
But it's not guaranteed that repeater comes from the same region, right? Because it could be-
I mean, it kind of, it's the same source. You can even measure the amount of electrons between you and the,
But then
The
it
repeater.
could be some large region where the right conditions for this burst to occur, and within that region.
yeah. It's not impossible, except that you measure the number of electrons at the part in 10,000, and some of them are around the burst, so because for reasons that we'll come to, and so you have various ways of telling that it isn't something else, and that's one of them. We can talk later. Other questions? Okay, so these fast radio bursts. The people like to talk about their fluence, which is their time-integrated flux. Their fluences are usually several Jansky millisecond or larger, most of the detected FRBs. A Jansky is a very large radio flux. Like a Jansky source is really bright. So they're a Jansky for a millisecond. The fact that they're bright for a millisecond is really helpful for us, because this means you can detect them with relatively, not the largest radio telescopes. And so in particular, let's say we put 4 10-meter radio dishes in space, then essentially they would be able to detect almost all FRBs that have been detected. So this would be their fluence sensitivity. Alternatively, you could put 4 meter dishes in space and have a 100-meter big collecting area on the ground. The 100-meter will get your electromagnetic template, which you can then use to pull out your voltage in the satellites, and that has the same sensitivity. And in fact, that might be the preferred way to go. So you could get by with relatively modest dishes in space to detect these. And actually, this answers maybe some of the questions. These are all the repeaters that Chime has detected as of a couple years ago. And this is their fluence. And this is how often they repeat above 5 Jansky millisecond. And so this is repeating every 100 hours, for example, above this relatively bright fluence. Okay.
What's that y-axis on that plot?
This is the repetition rate above 5 Jansky millisecond.
Per
So-
hour. What are the units on the y-axis?
Oh yeah, the hour minus 1. That's right. So this would be every hour. Okay. Okay. The next digression. We haven't said that many things far out in our solar system, and this is a list of at least all of the ones the U.S. has sent. And unfortunately, it takes a while to get things out there. And in particular, the record holder is this New Horizons satellite, which took 10 years to get out to Pluto at 34 AU. Of course, if you sent things in 2 directions, 34 AU, one direction, another, that's like a 70 AU baseline. So that would, as you'll see, that would be amazing. The Voyager 1, which we launched a very long time ago, is at 161 AU, and a lot of these outer solar system probes have pretty big radio dishes to communicate. For example, it had a 4-meter dish, and it was still communicating, except I learned very recently that that stopped in November. The Voyager 2 is still communicating. It's at 140 AU. Okay, so let's say we're detecting FRBs. We have with an instrument that's far out in the solar system. Unfortunately, the data rates for getting things back are not the most amazing for outer solar system probes. So could we even get the data back? So as an example, the New Horizons telescope, when it was at 40 AU, or the New Horizons spacecraft, I should say, at 40 AU, it had a 2-meter dish, and its standard rates for transmission back to Earth were 1 to 4 kilobits per second. Do we need something much greater than that, is the question, or can we get by with these minuscule data rates? Well, it turns out the key thing here is we only have to send back a millisecond of the voltages, and so the numbers work out. So if you're sending back a millisecond of voltages, then you need to send back about 4 million bits. If you do this over an hour, this is just a 1 kilobit per second, which is totally achievable. In fact, probably we have a bigger dish to send it back with. Okay, final digression. You guys have made it through, and this one is not the most serious, but this is an actual picture of a Tesla that is out on orbit out to Mars. And just very slightly more serious is that maybe it is the time to consider like these somewhat crazy ambitious things, in that the cost per launch has been plummeting. So for many years it was $10,000 per kilogram to get something out into space, and it's come down by at least an order of magnitude. And if I extrapolate, and I did a lot of math yesterday, and I found that it's almost to the point of me traveling to NYU. And in fact, when I account for your accommodations, I think it might even be cheaper. Okay, this is a good time to ask questions, and then we're going to start talking about measuring distances. Or make comments. Yeah? Okay. Okay, so we're going to switch terminology. We talked about this in terms of parallax, which is very related, but we're going to start talking about measuring distance in terms of detecting the curvature of the wavefront. So at my FRB, it emits light. The light, will travel out in shells, and if I can measure the curvature of the wavefront, then it tells me the distance to the FRB. Of course, if I have 2 detectors, I don't know the direction the source is coming from well enough, and so I can't constrain both the direction of the source and the distance via the curvature. And so in order to solve for both things, then I need 3 detectors. Of course, this is in 2D. In 3D, I have another angle, like there's another angle to the source, so I need a 4th detector. So you need 4 detectors in 3D to measure both the distance via this curvature and the angles. How are we doing this? Of course, we're just measuring the time the FRB arrives at the different detectors. Okay. And so in particular, we can calculate how big of an effect this curvature of the wavefront is. So my FRB light will hit a reference detector, and then it will hit a second detector. The time difference between it arriving at the second detector and the reference detector is, of course, just given by differencing the distances. And then you could do an expansion, and you can write this in terms of the direction that the source is coming from. This is the term that is usually kept in radio astronomy, for example. And then there's another term that owes to the curvature of the wavefront. And you can write this curvature wavefront as the baseline length squared with some projection divided by 2CD. D is the distance. And so then we can just evaluate. If I have detectors that are separated by 40 AU, and then this canonical 200 megaparsecs, then we're talking about a 20 nanosecond effect, this extra curvature delay, or converting that to distance with 6 meters. All right, so this is what we want to detect. Not only do we want to detect it, we want to measure it like very precisely to constrain distance precisely.
Sorry, I think you've already said this, but you also need to know the positions of your detectors, right?
Yeah, that's right. We'll come back to that.
Okay.
But that was the having detectors point at each other. And they could measure each other to centimeter was the
Right,
positions
but
of
when you
detectors.
measure an FRB, you have to know where the
Yeah,
detectors
I'll
are.
give an overview of how everything would kind of
Okay.
work together at the end. Yeah, but that's right. You need to know the positions of the detector. They're much better than 6 meters. Okay. All right. So, so we can just estimate like how well I can potentially measure distance. So my fractional error on distance is just going to be how well I can time my FRB signals divided by this curvature term. And so again, I'm just going to plug in, and I'm going to assume that I can time my FRB to the inverse of the frequency. And this is much of the rest of the talk is on that assumption. And in fact, actually, I think a better assumption might be 1/10 of the inverse of the frequency. Like it's something. This is potentially conservative. But if I assume the inverse of the frequency for how well I can time the signals, just plug in again for the same canonical values that we've been using, then for a single FRB you can measure its fractional distance to 2%, and which is of order the error that from all the Type 1a supernova that are 1.5% measurement of the Hubble constant. And so this is for a single FRB. Okay, but what underlay that statement was that I assumed we could time things to the inverse of the frequency, and so there's a variety of things that you might worry about that could affect how well we can time the FRB signals. And so we talked about how well we can align the waveforms in time time their arrival on the detector, which is the VLBI timing errors of order 1 over the inverse of the bandwidth. But you might also worry that my FRB light is going through a plasma. The universe is a plasma. There are going to be plasma propagation effects. There might also be gravitational time delays. Are these going to contaminate this measurement? Okay, so it turns out that there are 2 plasma effects that you might worry about. The lower order effect is called dispersion. Just the basic idea is higher frequency light traveling through a plasma travels closer to the speed of light than lower frequency light. So actually, when you detect an FRB, it really sweeps across in frequency. So the higher frequency, this is actually an FRB. The first FRB that was detected, like it arrives at 1.5 gigahertz much earlier than it arrives at 1.2 gigahertz. So you have this sweep. This is actually how we first found FRBs, because the sweep is telling us how many electrons the FRB light traveled through, and so the fact that it sweeps so much was telling us that it might not be in our galaxy. It might be cosmological. Okay, but this delay from not traveling at the speed of light is potentially a problem, because then if we don't know how fast it's traveling through the plasma, we don't. It's going to complicate us measuring the distance. Okay. And so in particular, the complication is the differential difference in electron column between the 2 sightlines. So I have my FRB arriving at 1 detector, and it goes through 1 column of electrons, and then the FRB arriving at another detector, the same light, goes through a different column of electrons. And we don't want the differential effect to be bigger than the inverse of the frequency, for example. The differential delay. And so so it turns out though that because this effect this delay scales as frequency to the -2, you can take it out. So the light will arrive at 1 detector a little bit earlier or later because of the plasma, but it will do this in a frequency dependent manner, and so you can fit for this delay because of its frequency dependence in addition to the geometric delay. And actually, this is done for GPS. So your phone wouldn't know its position on Earth to 20 meters if the GPS satellites didn't broadcast at 2 frequencies. But because they broadcast at 2 frequencies, you can essentially perfectly remove the effect of the ionosphere. Of course, spitting out increases error, and so when in order to fit out this effect, the error in how well you can time the FRBs is changed by essentially the frequency divided by the bandwidth. And this is propagated into the calculations that I'll show you in a bit.
If you were going through a constant and the same
Yeah,
electron distribution, because it's inhomogeneous,
yeah,
then I would believe this, but it's actually moving in time. Like for the
yeah,
GPS, it's really complex because
yeah,
the lines of sights are changing, and
yeah.
even in your application, they'll be going through different parts of the solar plasma and so on, so on. So how do you deal with that? You can't take out just by (-2).
Oh, it actually enters as just a phase. So like your electric field, at one detector in frequency is just modulated by some phase that depends on the electron column, this TM. That depends on frequency, and so it doesn't really depend. Like even if I throw it, like I just move in some electrons in front of one one sight line, like it appears in a way that you can fit out the.
Maybe it'll be clearer later when we see how you're fitting, but
It might not, because we don't talk about it. I'm not going to go into it in much more detail, but or how, I guess maybe I'll ask you a question, which is how is this different for GPS compared to
well, I don't know how it
Yeah.
works for GPS, and
Yeah.
so I'm a little at a loss. But
Yeah,
that's
yeah.
why I was thinking it might actually be worse for GPS, and
Yeah.
therefore I was thinking if it does work for GPS, there's something I'm not understanding. But a
Yeah.
priori, I would have thought that it was, in some approximation that stuff is constant, then you
Yeah.
can do it.
But what
And
I think
maybe
it
the
doesn't.
GPS
I
is
guess
so short timescales that
yeah, so the FRB light is coming over a millisecond, so it's not like the electron column is really changing in front. The sight line is like it's just a snapshot.
And so even though you're gonna do it many different times, you think you can take it out
Yeah.
each time? It'll be different every
It'll be different
time.
every time, so you'll have some phase that's different every time, but
Yeah,
but it
some
appears
phase
in a different way. And actually for GPS, it's not even an error once you have two frequencies. You're able to perfectly remove it by using two frequencies, and because then you can just solve for both the geometric delay and the plasmic delay. Yeah. Okay, yeah, we can come back to it. Okay, so there's a second plasma effect, which is called scattering, which is a higher order effect. And so the scattering rather than so I have my FRB, and its light, rather than thinking about it as traveling one path, light will actually travel many paths through the galaxy. If there are inhomogeneities on small enough scales, that the light that travels one path its phase will advance faster than light that travels other paths, and this can cause it to interfere at the end. And so especially the interstellar medium of our galaxy can act like a multi-slit experiment kind of. And so the different paths are diffracted in different ways and interfere and affect what the observer sees. And in particular, what this does is it smears out pulses. And so your FRB light, or in this case, it's a pulsar that's observed at different frequencies. So this is a higher frequency, and as you go down in this plot, lower and lower frequencies are shown, and the pulse is smeared out because this effect is larger as we look at the lower frequencies here. And so the same thing happens for the FRB. Its light will be smeared out, and so we won't be able to time its arrival as well to the extent that this effect is operating. And so this effect is well understood by studying pulsars. And so the scattering time, if you're looking out of the plane of the galaxy, is about 1/10 of a microsecond at a gigahertz. And you can see it has this really strong frequency dependence. So as you go up in frequency, the scattering time gets much smaller. And so if we want to be able to time our FRB signal to less than the inverse of the frequency, then this makes it so that we have to observe frequencies greater than 3 gigahertz. If we have at frequencies less than 3 gigahertz, this effect is just too big. So we're forced to observe somewhat higher frequencies than most FRBs have been observed. So it's forced to be somewhat higher frequencies.
So but this
Yeah.
this is because you don't know tau, or there's a spread that makes it harder to localize. Like how does this come in?
Yeah, it makes it so that the electric field, so if things were perfectly refractive, then the electric field arriving at one of your dishes will be exactly the same as at the other dish. But because of this, because it's traveling multi-paths, it's kind of like a path that bows out further. The electric field will have more delay in it versus a more direct path. And so the voltage time series is smeared out by this scattering, and so it makes it so that you no longer can time the arrival time of your FRBs as well. Like it's taken your light and it has smeared it out in a way that you're no longer able to time it as well. Does that?
Okay, and like infinite signal to noise, you would
Yeah.
still be able to cross-correlate it, but you're not in that.
So in infinite signal to noise, yeah, you're right. You could always then look for the where the two signals align the most.
Yeah.
But the correlation function of the voltages will smear out because of this
And
and
then,
make it harder.
yeah, okay.
Good, yes.
How do we know these inhomogeneities are from the ISM rather than like nearby the source itself?
So it turns out that if it's nearby the source, it doesn't matter. Then if effectively because you're not resolving the source, the light from the source is that both of your instruments are seeing is the same. So
What about the first order effect that you talked about previously? I mean, doesn't that also diffraction just depend on the line integration of the number density of electrons?
yeah, so the total effect doesn't matter for the dispersion. It's only the relative effect between your two sight lines, and so the overall delay from dispersion is not an important effect, which is and the overall delay for cosmological sources is of order a second. But that doesn't cause an error. Okay. How am I doing on time?
You've got about a little less than 15 minutes.
Okay, so those are the plasma effects. The next effect you might worry about is gravitational time delays. So your FRB light it might go by a star, or it might go by a galaxy, or again, a galaxy has a halo of dark matter around it, and this will impart some delay. And so again, it's the differential delay. You'll have a different sight line that will be either fall a little bit closer to the galaxy or a little bit closer to the star. And so will be more delayed than the sight line that's further away.
This is Shapiro we're looking at?
Yeah, this is
Okay.
Roman Shapiro. And so it turns out if you just send a skewer out of the plane of the galaxy, that will typically come within a light year of a star. And it turns out that this effect is only really important at very large baselines. So I'm going to stick in very large baselines, so 100 AU here. And let's say if you go if you are 1 light year from a solar mass, then this is it's still pretty small, 0.3 nanoseconds, and it has a quadrupolar dependence. So that potentially, if you had 6 detectors, you could actually just take this out because of this dependence. Kind of surprisingly, if I just send a skewer through the universe, it will also go on average past the 10 to the 13 solar mass halo within 1 million parsecs. And if you evaluate that, it gives you about the same delay. But the takeaway is this is relatively small, and it's potentially removable if you have enough detectors. Okay, so this is the summary of all of these different time delays. So the y-axis is time delay, x-axis is baseline length. What we want to detect is this curvature term. So this is the curvature delay.
So excuse me. So
Yeah.
there's nothing here which comes from solar system, because this, like in usual FRB,
Yeah.
here the satellites at very different places in solar system. Like
Yeah.
Solar wind, stuff like that?
Yeah, the solar wind is actually in this dispersion, in the electrons.
Okay, so
That's
that,
right.
that can be removed.
And that can be removed, yeah, that's right. That's right, that's, and I don't believe it enters anywhere else, you're right. Okay, so this is if a FRB is at 100 megaparsecs, this is the curvature if it's at 1,000 megaparsecs. This is the dispersion that's removable with 2 frequencies, or a wide bandwidth. And here I'm showing things at 4 gigahertz. At 4 gigahertz, it turns out that one of the dominant sources of noise is still the scattering noise. This is the VLBI group delay, the gravitational time delays, and then at 8 gigahertz, it turns out everything is smaller. Most of these other than gravitational, the plasma effects are smaller, and so your sensitivity is better as you go up in frequency. And so this is kind of these are the predictions. So you take all of these numbers.
What was the VLBI group delay timing?
Yeah, it's just how well you can align voltages
alright.
between your 2 telescopes. So it's like roughly the inverse of the bandwidth.
Okay.
And here we assumed a bandwidth of a gigahertz, which maybe I didn't. Yeah.
Okay.
Or 20% fractional bandwidth. Okay. And so here are the estimates for how well you can constrain things. So let's start here. Let's say we had 25 AU baselines, and we're observing at 4 gigahertz, and the width of the band is how well you can constrain your detector position. So the top of the width is 9 centimeters error on your detectors. And so you can see that like 25 AU, you're at 100 megaparsecs, maybe your error is a couple percent. At the mean redshift of these SHU supernova, which is right here, for a single FRB, your error would be several percent. 50 AU, things get much better. 8 gigahertz, things get much better still because the scattering delays are the more important delay here, like setting your noise. So that goes away at 8 gigahertz. And so like truly like crazy delays, crazy measurements of the distance are possible as your baselines get long enough. Even 25 AU at 8 gigahertz and 200 megaparsecs. This is a 1% constraint. Whereas this is for a single supernova, we get of order an 8% measurement of the distance. So there's potential for this to be to be very helpful.
Didn't you say the power though in these FRBs drops the 1/2 power in frequency? Again,
Oh, the frequency dependence.
Yeah.
Okay. So one of the biggest uncertainties, and I think this is on my conclusions in this, is that we have mostly observed FRBs at 1.5 gigahertz. We know that some of the FRBs have a very flat spectrum. So the first repeater that was detected has a flat spectrum to 8 gigahertz. But the number of observations of FRBs at 4 and 8 gigahertz are dwarfed by the number of observations at 1.5, and so we know less about their properties, and so I think that is the biggest uncertainty in this. That said, we think that there are thousands of repeating FRBs, and we know some have a flat spectrum, and these are predictions for one FRB. Okay. So we're putting these satellites in the outer solar system. Hopefully it can do other things that are interesting too. And so we have a paper that came out a couple months ago led by Huangyu Zhao that's on constraining the clumpiness of the dark matter, and I'll talk about that on the next slide. It also might be interesting, we're starting to think about how you could use this to constrain microhertz gravitational waves, which are frequencies that are mid-band between LISA and the pulsar timing arrays. And we think that this instrument, if you just take your dishes and point them at each other and measure the distance between the dishes very precisely, should be sensitive to interesting levels of gravitational waves. Like an amazing fact is if you take 100 AU, detector separated by 100 AU, and I just take the strain that the PTAs measure at 10 nanohertz, and you multiply those, that's 10 centimeters. So if you can make your thing inertial, over a year time scale, then maybe you could even measure this. We think it's sensitive to the mass distribution in the outer solar system, maybe even at the millionth of Earth mass level. A millionth of Earth mass is also actually how much dark matter is flying through the solar system within 100 AU at any given time. It's able to resolve the emission from nearby pulsars. If you have 100 AU baseline, that's like 10 kilometers at a kiloparsec of physical resolution. There are arguments about pulsar emission. The problem with pulsars is they're much fainter than FRBs, so it's less clear how you get the data back. But maybe as you're sending your dishes to the outer solar system, when they're only an AU away, you might have higher data rates and be able to get more of the time series. Okay, so this is a little bit more about the clumpiness of dark matter idea. So we actually have two proposals for how this could work. One is this having two dishes on other sides of the solar system, and another that uses gravitational lensing. And so the basic observable for this idea is you have a repeating FRB, and there will be some arrival time at one detector and another detector, so arrival time difference, and that difference will change with time as dark matter clumps drift across your sight line. And so you're looking for how the difference in arrival time changes with time between repetitions, and the same thing for the two image system. It turns out that the two image system, when you're using gravitational lensing, this would be have similar sensitivity to putting your dishes 1,000 AU apart, but there's a humongous number of caveats that we found for this system that make us feel like we would have to be very lucky. You'd have to have a lens repeating FRB, only a part in 10,000 or 1 in 10,000 of all your cosmological sources is strongly lensed, and some other things. So we think that unfortunately we might not be lucky enough to have this configuration. But these are some forecasts for how well we think we could constrain dark matter with 20 AU baselines. And so this is the power spectrum of matter. This is like the lambda CDM model. The dashed is like is a nonlinear model for lambda CDM. This is wave number, and like this is what we think our sensitivity would be. There's actually two signals I'm not going to get into that you can measure, but one is sensitive to actually really large scales in cosmology. Like it would just measure the large scale power, and another, which is actually the rate of change of the changes of the delays, is sensitive to really high K.
How is it sensitive to low K?
Yeah, it's
How
actually
does that happen?
the sensitivity is the same as the lensing of supernova, or like it's the same sensitivity, the integral over the power spectrum of like supernova magnification constraints, and so yeah, it's just how
Is that like from
it's
the
a
number?
K-squared
It's
P
like
of
from
K.
the numbers of lenses, or what? How's that?
It's just because the large scale modes are actually more important at changing the delay these delays than the small scale.
Seems odd.
But yeah, this is even the case for lensing of supernova magnification constraints, which are almost actually able to detect lambda CDM, but the same weighting.
Okay.
And it's just a K squared P of K weighting of like, whereas density would be K cubed P of K. But yeah, it's weird. It is surprising, but it's true. Okay, so this is the basic idea. So we need 4 satellites, at least 4-meter dishes in the outer solar system. If we have a 4-meter dish, you probably want like a 50 or 100-meter dish on Earth that gives you a really high signal template to pull out the signal from the smaller dishes. The satellites need onboard clocks. The onboard clocks have to drift less than this kind of few tenths of nanosecond in the light travel time from us telling that, signaling to the satellite that an FRB has occurred to the light arriving at the satellite. Turns out that actually isn't, those clocks aren't that much more precise than are on GPS satellites, the atomic clocks you would need. The satellites have to point to each other and measure their distance to calibrate their array geometry. They would have to do this every several days, because it turns out that there are many ways that the satellites are being accelerated in the outer solar system, from the solar wind, from the sun varying it with time, from dust striking the satellites, from the satellites being charged, and Lorentz forces as they move through magnetic fields in the outer solar system. Kind of amazingly, when we calculated all of these acceleration sources, they're all like a centimeter per week squared. So if we want to calibrate the positions of our satellites on the centimeter scale, you need to measure the distances every week or so to constrain your geometry. And then, like the rest of the time, when they're not pointing to each other, they would point at these repeating FRBs. You'd find the best repeating FRBs and you'd measure the distance to one, and then cycle through to the next. And that would be that's the scope. So I thought there was no way in hell I would ever have funding to like pursue this further, but my colleague directed me to a NASA call that was unlike any call I had ever proposed to. And so I'm going to show you the YouTube video, and then it'll be my final slide. And unfortunately, let me pause it because I want shit.
You need sound?
I want sound, yeah.
I hear sound too.
So I think it must have been directed by like Michael Mann and Jerry Bruckheimer. Okay, and
So what is this an ad for, and where did it appear?
okay, let me just go through the conclusions quickly, and I'll take questions. So I don't know. I feel like it's not that crazy. I feel like we have the technology to execute this if we want to. Like even to a single FRB, sub% measurements seem potentially possible. And like if we want to be even crazier, the sensitivity scales with baseline separation squared, the curvature delay is quadratic in the separation. But not only that, I think that there's other interesting science this will do too. I would show you a little bit about dark matter. We're starting to work on some of the other ideas. All right, thank you.
Any more questions for Matt?
I mean, just,
Yeah.
so that will measure distance, right? But
Yeah.
you know the host of this curve because you need redshift or something like that.
Yeah, it's the same idea that to some you of course you would measure distance, but you would measure the angle, the direction on the sky amazingly well too,
I see.
like ridiculously well. And so you'd look in that direction, you'd find what galaxy it's in. And then I probably even on that plot of like kind of what the velocity error. So of course you'll never measure the velocity perfectly, and so this is kind of what the supernova people claim that their velocity error is something like 200 kilometers per second.
Yeah, that's like the random motions of the galaxy.
Yeah, that's
It's
right.
not even a velocity error. They know the velocity is much better than that, but the galaxy isn't moving
Exactly.
with the Hubble phenomenon.
That's right. So you can measure the Doppler shift very precisely, but then it's not. There's some Hubble flow error. So that's why you can even see like why did I concentrate on 100 megaparsec or 200 megaparsec? Eventually that gets too big that it's a problem.
How much is it gonna cost? Like, what is, I have no idea, like, is
Yeah,
that
I
the
think
same,
that's-
but is like that the same price as New Horizons, or is it like 100 times more? Like what?
You know, I think that's what we're trying to understand. I mean, maybe some solace I take in this plot, but yeah, I don't know.
Yeah, but are those missions dominated by the launch? Is that what dominates a outer solar system mission cost? I don't know.
Yeah, I
don't
think
know.
it's a large fraction,
It
but
is
that's
a
a
large
good question. Yeah, like at some level, to me, these feel like sending GPS satellites with dishes out in the outer solar system, and in this case, you're making a bunch of the same thing and sending them out. I could imagine that it's launch cost that is the most expensive, but I don't know. Yeah.
A lot of plots you were showing was the results, like percent precision for a single like measurement, right, of
Yeah.
FRB. But
Yeah.
you said that, right, there are many of them that you
Yeah.
can get, right? I mean, is it cheaper or more optimum to just go with like a weaker baseline and just get the large number of FRBs to counteract that?
Yeah, I think it could be. I think right now we are limited by the fact that we don't know as much as we would like to know about FRBs at 4 gigahertz. But it could be that I deleted a plot I've had in versions of this talk is there are expectations that there are something like 10,000 FRBs in the chime footprint that are repeating on 100-hour timescales. So it could be that there's just so many of these repeating FRBs that have sufficient emission at 4 gigahertz, and then then maybe you would go in that direction. Yeah, it's also, I feel like it would be really nice to have a 1% measurement of even for one
Right.
FRB.
Why haven't those 4 gigahertz FRBs been detected yet?
Yeah, one is that it's easier to find a lot of FRBs as you go to lower frequencies, just because the beam of your radio instrument is larger. So that's a major reason. Also, a lot of radio astronomy is done at a gigahertz. But in fact, those are the major instrument that's detecting most FRBs is this chime
Gotcha.
instrument, which is even less than a gigahertz.
Gotcha.
And it has like this very fast time, like not all instruments actually have fast enough cadence of their readout or whatever you call it in radio astronomy. Is that why chime found all these things, but
I
other
think
things
it's
didn't? Or is it just the aperture? It can't just be the aperture.
it's they have a lot of like synthesized beams on the sky, so they cover they phase up their it's these cylindrical dishes, but then dipoles. And so they can correlate the dipoles so that they point in many different directions, and they do this in like maybe even 100 synthetic beams at a time. So they cover a huge amount of the sky.
Okay, so it really is more A omega or whatever you would call it. Like
Yeah,
more,
that's right.
it's like they have a big aperture, but relative to like GBT, they cover, a single beam of theirs is potentially huge, like most of the sky.
That's right.
Okay.
What was, that,
Yeah.
that advertisement
Yeah.
was an ad for a NASA agency?
Yeah, they have a YouTube I don't know, clip on the proposal call.
And so you proposed, and what did you propose for?
I proposed for developing this further. Yeah, that's right. And yeah, so it's like it's a 1-year proposal where it's to do some of these estimates better.
Not to build a big radio dish that you launch.
Yeah, not
Yeah.
yet. Not yet.
Not yet.
Well, thank Matt again.
You're around all week,
I am, I'll be at the CCA on Thursday,
Oh, okay.
yeah.
I do wanna ask you about this dispersion.
Oh, sure,
Business
sure.
areas. And also, one thing you can immediately answer,
Yeah.
on GPS for your phone,
Yeah,